Welcome to Math Zone African Motives. In this tutorial, we're going to explore how to draw the sketch graphs of inverse trigonometric functions. By the end of this video, you will be able to first, use a systematic 6-step guide to draw any inverse trigonometric graph. And second, apply this guide to sketch the graphs of sine inverse, cosine inverse, and tangent inverse, including their asymptotes and key points. Let's dive in. First, let's understand why we use a special process for these graphs. When drawing graphs of inverse trigonometric functions, it's incredibly useful to first draw a rough sketch of the original function. We'll use this as a guide and then erase it later. So, a prerequisite for this is to be very familiar with the basic trigonometric graphs like sine, cosine, and tangent. Let's look at the guidelines provided in your textbook. We'll break them down one by one. We'll follow these 6 steps to sketch any inverse trigonometric graph. Step 1 is to determine the domain and range. This is a crucial first step. Remember that for an inverse function, the range of the inverse graph is the domain of the original graph, and the domain of the inverse graph is the range of the original graph. This swapping of domain and range is a fundamental property of inverses. This idea is so important, it's highlighted here. The range of the trigonometric function becomes the domain of the inverse function. The reason we need this is that a normal sine, cosine, or tangent function is periodic. To have an inverse that is also a function, we must restrict its domain to a specific continuous interval where it is 1 to 1. These are the standard restricted domains for the original functions, which you can see in Table 2.1. And here, in Table 2.2, are the corresponding domains and ranges for the inverse functions. We will use this table frequently. Now let's move on to step 2, marking the axes. Because our domains and ranges for these graphs are often in radians, we need to mark our axes appropriately. Label the axes with integers 1, 2, 3, and so on, but also mark the key radian values. For example, you should be able to mark pi over 2, which is approximately 1.57, and p, which is approximately 3.14. Knowing these approximations helps you place the points on the graph correctly because you have a familiar scale to work with. Step 3 involves the trickiest part of the process. The third step is to draw a rough sketch of the original function, and it's very important to use a dashed or dotted line for this. This sketch is a guide only. As the guidelines say, it will be erased after we draw the final inverse graph. You should only draw the part of the graph that corresponds to the restricted domain from Table 2.1. For example, for sine, we only sketch the part of the graph from x equals negative pi over 2 to x equals pi over 2. Step 4 is the core of transforming the original graph into its inverse. The fourth step is to look for convenient points on your original graph and mark their images. This is where you switch the x and y coordinates. For every point AB on the original function's graph, the point BA must be on the graph of its inverse. For example, if the original point is AB, the inverse point will be BA. A special case is if the graph passes through the origin, 0, 0, 0. If a graph passes through the origin, then its inverse also passes through the origin, because switching 0 and 0 doesn't change the point. Step 5 deals with a special feature of these graphs, asymptotes. The fifth step is to draw in the asymptotes. A vertical asymptote exists at x values where the function is undefined, and a horizontal asymptote exists at y values where the function is undefined. Here's a crucial rule. If the original graph has a vertical asymptote at x equals a, its inverse will have a horizontal asymptote at y equals a. This rule is particularly important for the tangent, secant, and cosecant functions. Just like key points, the asymptotes get swapped when you find the inverse. Finally, we bring it all together in step 6. The sixth and final step is to sketch the inverse graph. Using the key points from step 4 and the asymptotes from step 5, you'll connect the points to form the final curve. Make sure your graph approaches the asymptotes and has the correct shape. Once you have drawn the inverse graph, you can erase the original dotted sketch of the trigonometric function as it was just a guide. This leaves you with the final, clean sketch of the inverse trigonometric function. So, to recap the 6 steps, determine domain and range, mark axes, sketch the original, switch points, draw asymptotes, and finally sketch the inverse. You've got this. Let's apply our 6-step guide to our first example, the inverse sine function. Our goal is to sketch the graph of y equals sine inverse of x. Notice the problem gives us the range directly as negative pi over 2 to positive pi over 2. This is the standard restricted range for the inverse sine function. Okay, let's follow our 6 steps. Step 1. Determine the domain and range. We are given that the range of the inverse graph is the closed interval from negative pi over 2 to positive pi over 2. According to our rule, this range is the restricted domain of the original sine graph, y equals sin x. Now, what is the range of y equals sin x for this restricted domain? The range of the sine function is always from a 1 to 1. This means the domain of our inverse function, y equals sine inverse of x, is the closed interval from 1 to 1. Step 2. Mark the axes. We will create our Cartesian plane, marking the x and y axes. On the y-axis, we'll mark the key values of pi over 2, approximately 1.57, and negative pi over 2, approximately negative 1.57. On the x-axis, we'll mark 1 and negative 1, as these are the limits of our domain. We need to ensure our axes are scaled to fit both the domain from negative 1 to 1 and the range from negative pi over 2 to pi over 2. Step 3. Draw a rough sketch of y equals sin x for the restricted domain. We'll draw this as a dashed line. It starts at y equals negative 1 when x is negative pi over 2, goes through the origin, and ends at y equals positive 1 when x is pi over 2. The curve rises as x goes from negative pi over 2 to pi over 2. We'll label its endpoints. Step 4. Find key points on our original sketch and interchange their coordinates. We have 3 clear points from our dashed graph. Negative pi over 2, negative 1, the origin, 0, 0, and pi over 2, 1. Swapping the x and y values for each point gives us negative 1, negative pi over 2, 0, 0, and 1 pi over 2. These 3 points are on the graph of our inverse function, sine inverse of x. Let's mark these inverse points on our graph. Step 5. Draw in asymptotes. Looking at our restricted sine graph, are there any vertical asymptotes? No, the sine function is continuous everywhere. Therefore, its inverse sine inverse of x has no horizontal asymptotes. So for our final graph, we just need to connect the points. Step 6. We sketch the inverse graph. Starting at the lowest point and moving up, we connect the dots with a smooth, continuous curve. This solid red line represents y equals sine inverse of x. Finally, as instructed, we can erase the dashed sine curve. Let's compare our graph to the one provided in your textbook. They match perfectly. Our endpoints are correct. The graph passes through the origin and it's a smooth curve. We can confidently say our sketch is verified. So we have successfully drawn the graph of y equals sine inverse of x by following the 6 steps. Notice how this graph looks like the dashed sine curve on its side. It's a reflection across the line y. Now let's tackle our second example, the inverse cosine function. Again, we'll use our 6-step guide. Let's start with step 1. Step 1. Domain and range. First, let's find the restricted domain for the original cosine function, y equals cos x. Looking at our table, the restricted domain for cosine is the closed interval from 0 to pi. The range of y equals cos x for this domain, just like sine, is the interval from 1 to 1. This means the domain of our inverse function, y equals cos inverse of x, is also the closed interval from a 1 to 1. Step 2. Mark the axes. We will mark the x-axis from 1 to 1 and the y-axis from 0 to pi, which is approximately 3.14. A key value to mark on the y-axis is pi over 2, or approximately 1.57. Step 3. Draw a rough sketch of y equals cos x. For the domain 0 to pi, the cosine function starts at its maximum value of 1, passes through 0 at pi over 2, and ends at its minimum value of 1 at pi. We'll sketch this with a dashed line. We must only draw the portion of the cosine graph between these two x values to ensure its inverse will be a function. Step 4. Find key points and interchange their coordinates. Let's pick 3 easy points from our dashed cosine graph. The y-intercept, which is 0, 1, the x-intercept, which is pi over 2, 0, and the endpoint pi negative 1, 1. Now we swap the x and y coordinates for each. The point 0, 1 becomes 1, 0. Pi over 2, 0 becomes 0, pi over 2, and pi, negative 1 becomes negative 1, pi. These 3 points define our inverse cosine graph. Let's plot these 3 points on our axes. Step 5. Check for asymptotes. Like the sine function, the cosine function on the interval 0 to pi has no vertical asymptotes. Therefore, its inverse, the inverse cosine function, will have no horizontal asymptotes. Step 6. Sketch the inverse graph. All we need to do is connect our 3 points with a smooth curve. It will start at the point 1, 0, travel through 0, pi over 2, and end at negative 1 pi. This gives us the complete sketch of y equals coas inverse of x. Finally, we can erase our dashed guide graph of cosine. Let's verify our graph against the provided memo. As you can see, our graph of inverse cosine is identical to the one in the notes. The key points are correct, and the shape of the curve is accurate. Our sketch is verified. So, we've successfully graphed the inverse cosine function. Notice this graph also looks like the original cosine graph reflected over the line y(x), but its range is limited to the first 2 quadrants, from 0 to pi. Our final example will be the inverse tangent function, y equals tan inverse of x. This one will be a bit different because it involves asymptotes. Let's apply our trusted 6-step guide. Step 1. Domain and range. First, the restricted domain for the original tangent function, y equals tan x, is the open interval from negative pi over 2 to pi over 2. The range of tangent over this domain is all real numbers, which we write as the open interval from negative infinity to positive infinity. This means the domain of our inverse function y equals tan inverse of x is also all real numbers. Step 2. Mark the axes. We will mark our x-axis with standard integers and our y-axis with pi over 2 and negative pi over 2. Note the parentheses on the range of y equals tan inverse of x, which tells us that the asymptotes will be at these y values. Step 3. Draw a rough sketch of y equals tan x. Remember, the restricted domain is from negative pi over 2 to pi over 2. The tangent function goes to negative infinity as it approaches negative pi over 2, goes through 0 at the origin, and goes to positive infinity as it approaches pi over 2. We sketch this as a dashed green line. Step 4. Find key points. The tangent graph has an x-intercept at the origin, 0, 0. If we want a few more points, we can use the special angles pi over 4 and negative pi over 4. We know that tangent of pi over 4 is 1, and tangent of negative pi over 4 is 1. This gives us the points pi over 4, 1, and negative pi over 4, negative 1 on the original graph. Now we swap the coordinates. The origin stays at 0, 0. Pi over 4, 1 becomes 1, pi over 4. And negative pi over 4, negative 1 becomes negative 1, negative pi over 4. Let's mark these 3 points. Step 5. Draw in the asymptotes. This is the new part for tangent. Our original dashed graph of y equals tan x has vertical asymptotes at x equals negative pi over 2 and x equals pi over 2. Following our asymptote rule from earlier, we swap the variables. This means the inverse function, y equals tan inverse of x, will have horizontal asymptotes at y equals negative pi over 2 and y equals pi over 2. Let's draw these as dotted lines on our graph. These horizontal lines define the upper and lower bounds for our inverse tangent graph. Step 6. Sketch the inverse graph. We need to connect our key points with a smooth curve that approaches the horizontal asymptotes y equals pi over 2 and y equals negative pi over 2. As x goes to negative infinity, y gets closer and closer to negative pi over 2. As x goes to positive infinity, y approaches pi over 2. The graph smoothly rises from left to right, crossing the origin. This gives us the complete sketch of y equals tan inverse of x. Now we erase our green guide graph of tangent. Let's compare our graph to the one in your notes. They are identical. We have the correct horizontal asymptotes and a curve that passes through the origin. Our sketch is verified, and there you have it. We've successfully sketched the graphs of sine inverse, cosine inverse, and tangent inverse using our 6-step guide. We have seen how domain and range, key points, and especially asymptotes are swapped between a function and its inverse. This guide you've learned today is a powerful tool. It allows you to sketch the graph of any inverse function, not just the inverse trigonometric ones, as long as you can graph the original function. Thank you for watching this tutorial from Math Zone African Motives. If you found this video helpful, please give it a thumbs up. We encourage you to practice these steps on the remaining inverse trigonometric functions, like cosecant inverse, secant inverse, and cotangent inverse. The process is the same. Subscribe for more tutorials from Math Zone African Motives.